topic in our unit on energy and momentum, the culminating topic for the momentum perspective, the momentum part of our unit, 4.6, conservation of momentum. So again, please ignore these announcements. This video was recorded before this lesson was actually done in class. So we're up to today. What happens to momentum when objects interact? How can we predict the outcomes of collisions, crashes, and explosions? So conservation momentum, okay? Let's see what we have right here. So that's a lab we were doing in class, okay? So conservation momentum is very similar to conservation of energy in that in closed systems where the forces come from objects interacting, such as crashes and explosion, the momentum of the system is conserved. So the momentum before a crash is the same as the momentum after a crash. And what's happening here is that momentum is not lost or destroyed or taken out of the system, but rather momentum is simply exchanged between the objects in the system. So if one object loses momentum in our system, another object will pick up that momentum. So there's momentum transfer happening just as there's energy transfer happening. In open systems, there are forces where there are forces not coming from the objects themselves, so that means forces from outside of the system. The momentum of the system can change. And this happens if friction or air resistance acts very similar to what we saw with non-conservative forces with energy. Okay? So a very useful way to think about conservation of momentum is with the what we call the money analogy. Okay? So the idea behind conservation of momentum and the money analogy is, let's say we have two people, Jack and Jill, who both start off with $100. Okay? So their total amount is $200. So let's say Jack and Jill interact, and Jack gives Jill $50. So this is like our collision here, okay? So as a result, Jack is going to have $50 after the collision / interaction, and Jill is going to have $150 after the collision interaction. So Jack has lost money while Jill has gained money, all right? However, the overall amount of money in the system hasn't changed. And so as a result, this is very similar to conservation of momentum. When two objects collide, say one object is Jack, Jack can lose momentum, but that momentum is not destroyed, it's just transferred to Jill. And so the overall momentum, the sum momentum of the whole entire system remains the same. So here's a think, pair, share for y'all to consider, okay? An astronaut is stranded from their space station located to the left. Let's say it's located to the left of our astronaut, so our astronaut's right here, our space station is to the left. In order to return to the space station, the astronaut throws a wrench to the right. After being thrown, does the person or the wrench have more momentum? Explain your response. Which object moves at a faster speed? Explain your response again. So take a moment to think about this and answer, and then we'll go over it together as a class. All right, so let's take a look at A here, okay? So if our person throws this to the left and our person, as a result, moves to the right, we want to know how does the momentum of each object compare, okay? So we know that this system initially, if they're floating out in space, not moving, is going to have initial momentum of 0. So since that's our initial momentum, that momentum must remain the same. So we must have 0 momentum after the wrench is thrown. So as a result, if the wrench is moving to the right with a certain amount of momentum, that means that the person must be moving to the left with the equal amount of momentum. So, as a result, each object will have equal amounts of momentum that cancel each other out. Remember, momentum has direction, resulting in the net momentum remaining as 0. Okay? So, there's the first explanation. We can look at it. Okay? So each object exerts an equal force on each other over an equal amount of time. So equal force comes from Newton's third law. An equal amount of time comes from the fact that, well, time is the same for both objects. So the momentum of each object must be the same. The other way we can look at it from the perspective of conservation momentum is, again, that the moment before the wrench is thrown is 0. So as a result, each object after the wrench is thrown must have equal but opposite momenta after being thrown. The wrench has a certain momentum to the right, and the person has an equal but opposite momentum to the left. And when you combine those two momenta, the momentum of the person and momentum of the wrench, that gives you 0. Even if we don't know what the specific numbers are. In B, we ask which object moves at a faster speed. Now explain, okay? So we know both of these objects are going to have equal amounts of momentum, okay? So now we need to be thinking about the masses of each object, okay? So they have equal amounts of momentum, but the astronaut has more mass than the wrench, which means the astronaut has more inertia. So as a result, because our astronaut has more inertia, that means by Newton's first law, the astronaut's going to move slower and the wrench will move faster. So now let's consider the following. In which of these scenarios shown is momentum conserved? All right, and let's say we're neglecting friction in these scenarios here. So let's put this up on the screen to watch. Watch it on YouTube here. A YouTube video within a YouTube video.
Toyota or Nissan. Get 0% APR for 72 months on the Tucson.
In Wrecking Ball Baloney, Adam and Jamie start small.
You need to stop playing with your balls and get back to work.
Then get bigger.
Oh, that's cool.
And bigger.
What does a Heinemann dream about at night? This.
And bigger again.
When I was but a wee child, I never imagined that the construction of 5 wrecking balls would be something I could put on my resume one day.
And like kids in a candy store, once their colossal cradle was built...
Well, I think there's only one thing left to do.
What's that?
Hook it up and try it.
They couldn't help but put it to a slightly odd set of tests. So sit back and enjoy the Mythbusters Newton's Cradle being put through some surreal swings. But having got fruity, the real testing could begin.
That is a good day's work.
Yep. Can't wait to see it work.
Neither can I. Let's come back tomorrow and do the test.
Okay.
So we can see in one case right here, we had a very small Newton's cradle. Newton's cradles are those little toys that you may have seen where essentially little wrecking balls hit back and forth on each other and they swing back and forth in seemingly perfectly harmonic motion. So harmonic in the sense of nice and good to look at, not harmonic in the physics sense of the word. So what they did in this case is we had the smaller version where the smaller version worked perfectly. It seemed like there was this nice smooth harmonic motion going on, and then they had the larger version which was chaotic and it didn't seem like it's very smooth, and it didn't work very well. It wasn't very efficient, okay? So we may ask in which case is momentum conserved, and it may seem like momentum is not conserved in the larger case. However, in both cases, momentum is actually conserved, okay? In this case, momentum is conserved in all collisions where no outside forces act. What's happening here is that momentum is conserved, but a different quantity is not being conserved, okay? And that quantity is the kinetic energy of the objects, okay? So let's take a look at a little bit what's going on here and what's happening with elastic and inelastic collisions, okay? Let's see what's going on right here. So, inelastic collisions, okay? In crashes, explosions, and collisions, momentum is always conserved, but kinetic energy may not, okay? If kinetic energy is conserved, the collision is considered elastic. If kinetic energy is lost or the objects stick together, the collision is considered inelastic. Kinetic energy is converted into different forms of energy, okay? So an example right here would be a ball rebounding off of the ground. So the ball loses kinetic energy when it collides with the ground at right. So the collision is inelastic, and that's indicated by the fact that each time the ball bounces off the ground, it's going to reach a lesser and lesser maximum height. So why is it that momentum is conserved, but kinetic energy is not conserved in inelastic collisions? So the reason being is that momentum only has one form. Momentum can't be converted from, say, heat to anything else. Momentum is always momentum. So even in the collisions, momentum is still there. It's just being spread out throughout, through, say, all the Newton's cradles balls, or through the basketball on the ground. Okay. However, kinetic energy can take many different forms, as we've seen. So, for example, right here, when our basketball collides with the ground, momentum is transferred from the basketball to the ground, and momentum is still conserved. However, kinetic energy is not conserved because kinetic energy is being converted to heat every time the ball hits the ground, which is why our kinetic energy is getting less and less. Our basketball rises to a lesser and lesser maximum height each time it hits the ground. So momentum can only take one form, and it will always be conserved in collisions, whereas kinetic energy can be converted into different forms of energy, such as heat, and thus will not always be conserved depending on the conditions of your collision. So let's do a quick check for understanding here. When two cars are in collision, what happens to the momentum of each car? All right, the cars stick together now, and heat is generated by the collision. Is this an elastic or inelastic collision? So take a moment to think about it, and then we'll go over and answer together. So the momentum of the two cars are exchanged. The total momentum of the system overall remains the same. The car that's doing the rear ending is going to lose momentum as it transfers momentum from itself to the car in front of it. Now, this would be considered an inelastic collision because 1, the cars are sticking together, and 2, heat is generated. And we know heat is a form of energy, which tells us that some kinetic energy from the silver car is being converted to heat in the midst of the collision, thus telling us that this is an inelastic collision. So let's look at how to do some conservation of momentum problems here real quick. All right, let me bring this on over here. So let's take a look here, okay? A 0.005 kilogram bullet is fired horizontally with a speed of 1100 meters per second by a 6 kilogram rifle that is initially at rest. What is the speed of the rifle when it recoils? So the problem-solving process with this is very similar to conservation of energy problems. So first thing that we're going to do here is we're going to write down the masses and velocities of each object before the collision explosion. So we have that the initial mass of our system is going to be 6 plus 0.005 or 6.005 kilograms because both our bullet and the gun are combined. And the initial velocity is 0 meters per second because both the gun and the bullet are at rest. So now afterwards, the gun and the bullet are going to separate. The bullet's going to have a mass of 0.005 kilograms, and the velocity of the bullet is going to be 1100 meters per second. Now the mass of the gun is 6 kilograms, and the velocity of the gun is what we're interested in finding here. Okay? So now what we're going to do is we're going to set our initial momentum equal to our final momentum. And so our initial momentum is going to consist of just the initial momentum of the gun and bullet together. So that's going to be mi, our initial mass, times vi, our initial velocity. So 6.005 kilograms times 0 meters per second. And then that's going to be equal to the momentum of the bullet plus the momentum of the gun after being fired. So that's going to be mass of the bullet times velocity of the bullet plus mass of the gun times velocity of the gun. So that's going to be 0.005 kilograms times 1100 meters per second plus 6 kilograms times the velocity of the gun. So as a result, we're going to get 60.05 equals 5.5 plus 6 times Vg. So as a result, we're going to get 54.55 equals 6 times Vg. And as a result, we're going to get the velocity of the gun equals 9.09 meters per second. So that's how fast the gun is going to recoil with. And if you've ever noticed a gun recoil before, this is an application of conservation of energy in Newton's third law, okay? So again, to reiterate our steps, and I forgot to go through the other 2 steps, we write down the masses and velocities of each object before collision/explosion. We write down the mass and velocities of each object after collision/explosion, which is step 2. And then you use conservation of momentum to determine our unknown quantity. So again, very similar to steps that we use for conservation of energy problems. So let's take a look at one more example here before we do a check for understanding. So let's say we have a billiard ball with a mass of 1.5 kilograms that is moving at 25 meters per second and strikes a second ball with a mass of 2.3 kilograms that is motionless. We want to find the velocity of the second ball if the first ball stops when it strikes the second ball. So again, we proceed by writing down the masses and velocities of each object before the collision / explosion. So in this case, we're going to say the mass of the first ball before the collision, so m1b equals 1.5 kilograms, and the velocity of the first ball before the collision, v1b equals 2.5 meters per second. Now the mass of the second ball before the collision equals 2.3 kilograms, and it is at rest, so it's going to have initial velocity of 0 meters per second. Now after the collision, okay, we're going to have the mass of the first ball after collision, m1a, is equal to 1.5 kilograms, and it's come to a stop, so its final speed is going to be 0 meters per second. Next, we have m2a equals 2.3 kilograms, and we're going to have v2a equals 0 meters per second, okay? So our second ball's mass after the collision is going to be 2.3 kilograms, and its final velocity is actually going to be unknown. I have 0 meters per second here, but that is a mistake. That should be an unknown right there because that's what we're trying to find here. So now we start off by summing the initial momentum of our system before collision, so P1b plus P2b, and we set that equal to the final momentum of our system after collision, P1a plus P2a. So that's going to give us m1b times v1b plus m2b times v2b equals m1a times v1a plus m2a times v2a. So this momentum right here, the m2b times v2b is going to be 0 because v2b is 0. The m1a times v1a is going to be 0 because v1a is 0. And so now we can start plugging in numbers. m1b is 1.5, v1b is 25, so we're going to get 1.5 times 25 equals 2.3 kilograms times v2a. So as a result, we're going to get 37.5 equals 2.3 va, or v2a, which tells us that our final velocity of our second billiard ball, if we divide both sides by 2.3, is going to be 16.3 meters per second. And thus is how we would solve a conservation of energy or momentum problem, okay? So if the objects are separate, the momentums are going to be separate. If the objects are together, the initial momentum or final momentum, whenever they're together, is going to be just one overall momentum. So now let's do one problem as a check for understanding. So a bullet with a mass of 0.005 kilograms is moving at 500 meters per second when it strikes and sticks on a block of wood that has a mass of 5 kilograms. We want to know what is the final velocity of the wood/bullet mass. Alright, so again, take a moment to work on this, proceed through the steps, and we'll bring it back together. And then if you get stuck, we'll bring it back together and discuss how to do this problem together. So let's take a look at this problem right here. So the mass of the bullet is going to be 0.05 kilograms, 0.005 kilograms. So that's the mass of the bullet. The velocity of the bullet is initially 500 meters per second. And then the mass of our piece of wood is 5 kilograms. So MW is 5 kilograms. And the velocity of the wood, VW, is 0 meters per second. It's at rest. And then afterwards, they're going to be combined, so we can call this M final or M after, whatever we want. It's going to be 5.005 kilograms since they combine. And then our final speed is going to be our unknown. Okay? So now we combine our momentum initially, so we're going to have the momentum of the bullet plus the momentum of the wood equals the final momentum of the system. So that's going to be the mass of the bullet times velocity of the bullet plus mass of the wood times velocity of the wood. The velocity of wood is 0, so this right here is going to be 0 right here, the second term. All right, the initial momentum of the wood. And then we're going to have the mass of the final objects together times the final velocity of the objects, okay? So that's going to give us 0.05 kilograms, or 0.005 kilograms, times 500 meters per second equals 5.005 kilograms times VF, or 2.5 equals 5.005 times VF. Dividing both sides by 5.005 yields that our final velocity of the system is going to be 0.499 meters per second, or approximately 0.5 meters per second. And thus is how we solve our practice problem here for conservation of momentum.